So, welcome you to this module. So, last module we introduced invariant tests. We talked about under what conditions we would say that a given testing problem is invariant under a group of transformations. Now, then we said that if a testing problem is invariant under a group of transformations G, then it makes sense to consider only invariant tests. So, we introduced the concept of an invariant test. That means V of x should be same as V of gx for every g. So, in general I can talk about the concept of a, because any test function is only a function of observations x. So, it is a statistic. So, I can talk about the concept of any invariant statistic. So, that means I would say that a statistic T is invariant if T of x is same as T of gx for every g and for every x. Then we related it to the concept of a sufficiency, that sufficiency helps us in reducing the data. In the same way, invariance also helps us in reducing the data, because it says you should consider only those statistics which depend on observations in such a way that T of x is same as T of gx. For example, in the location case, what it would have meant is T of x is same as T of x plus c. That means T of x is same as T of x1 plus c, x2 plus c, and xn plus c. C I can take as minus xn, so that means T of x is same as T of x1 minus xn, x2 minus xn, and xn minus 1 minus xn. That means T should depend on observations only through x1 minus xn and xn minus 1 minus xn. So, it reduces the data. It just says that you do not have to consider the whole of x1, x2, xn, rather you restrict only to x1 minus xn and xn minus 1 minus xn. So, from n dimensional data it has reduced the data to n minus 1 dimensions, x1 minus xn to xn minus 1. So, the way we talked about the way sufficiency helps us in reducing the data, invariance also helps us in reducing the data. So, we had a concept over there, the statistics, which gives you a maximal reduction. We call that as a minimal sufficient statistic. So, here I can talk about a statistics which is most invariant or maximal invariant. So, we talked about the concept of a maximal invariant statistic. And what are the requirements for a maximal invariant statistic? It should be invariant. That means T of x should be same as T of gx for every x in Rn, and g is in G. And it should be maximal invariant. That means if T of x1 is same as T of x2 for some x1 and x2 in Rn, then x1 should be related to x2 through some g, for some g. Then we talked about the concept of a maximal invariant functional, because if my original script P is invariant under G, it induces a group of transformation on P, which is G bar. So, I talked about maximal invariant functional. On the class of all distributions P. And I gave you, I explained you what do you mean by a functional. A functional is nothing but a function whose domain is a class of functions. So, maximal invariant functional is one which is invariant first of all. That means theta of f1 should be, theta of f should be same as theta of g bar of f for every g bar. And then it is maximal in the sense that theta of f1 is equal to theta of f2 should imply that f1 is g bar of f2 for some g bar. Then we did a result which says that Tx is maximal invariant if and only if any other invariant statistic is a function of this maximal invariant statistic. So if any other invariant statistic is a function of Tx, or in other words, for any other invariant statistic Vx, there exists a function h such that V of x is same as h of Tx. Then we saw that distribution of maximal invariant statistics depends on f only through, depend on f belonging to P only through maximal invariant functional theta of f. Now, if you see these two results, it says that if you look at any invariant statistic, it would be a function of maximal invariant, and distribution of maximal invariant depends on the maximal invariant functional. So, if you combine the two results, you conclude that distribution of any invariant statistic will depend on maximal invariant functional theta f. So, this you write down as a remark. Distribution of any invariant statistic. So, in particular the invariant test, because invariant test is a invariant statistic, phi of gx is same as phi of x. In particular, invariant test phi in di alpha depends on f only through maximal invariant functional theta f. So, note that although your original problem of testing was h naught f belongs to P0 against h1 that f belongs to P1. In many situations, what may happen is, you know that if you consider any invariant test, it depends on f only through theta of f. So, in many situations, you will be able to write down this hypothesis h naught and h1 in terms of a theta of f, because that is what is going to matter. So, in many situations, so this gets transformed to h naught star or h1 star, theta f belongs to P0 star, or theta f belongs to P1 star. Because f is not going to play a role, because if you are considering only invariant test depends only on theta f. Sorry, invariant tests depend on f only through theta f. So, testing f belonging to P0 would be equivalent to testing that theta f belongs where, because that is what it matters. And once I have written down hypothesis in that sense, in many situations this theta f may turn out to be a real parameter. So, if theta f is real parameter, finding UMPI alpha test is possible. So, that is the whole scenario. So, this invariance helps us in reducing the class of tests under consideration. So, we in certain situations will be able to find the best tests. So, to see one such application where I will not be able to find possibly the UMP alpha test or UMPU alpha test, let us consider in general estimation of testing location family. So, what may happen is in many times you may get a feel through your histogram that your data is bell-shaped. That means its shape is like a bell, as is for the normal distribution. But many distributions look like a bell-shaped, and they may not be normal. So just by looking at the shape that it is bell-shaped may be sometimes confusing. And then one may say that, look, it could be bell-shaped. Second may say that, no, it is another bell-shaped, some other distribution. So it could be normal against something which looks normal, but its kurtosis may be different, and so on. So let us consider one such problem which belongs to the location families. So my H naught is that f belongs to P0, H1 is that f belongs to P1, where P0 and P1 both are location families, but the different location families. One could be, for example, normal, the other could be Cauchy. But what I know is those parameters are unknown. So it could be normal theta 1 for some theta, or Cauchy theta 1 for some theta. So my P0 is collection of all those f0 thetas, such that theta belongs to capital theta, which is R. P1 as f1 theta, such that theta belongs to theta again, which is R. So two different parametric families, and where my fi theta, fi theta x is a vector. This is nothing but fi of x1 minus theta, xn minus theta. For some, theta belongs. I is equal to 0. So for example, P0 is f0 theta. So that means it is some location families, because theta is a location parameter. So it could be that you are dealing with a normal over here, IID normal, theta 1. F1 theta is some other PDF. It is also location. Fi theta is nothing but fi of x1 minus theta, xn minus theta. So this fi is different, f0 and f1. So this fi theta could be for Cauchy, for example. And what you are interested in is that your data is coming from a normal distribution with some unknown mean theta. Against that, data is coming from a Cauchy family with some unknown location parameter theta. And that is what you want to test. Now, in the location case, we know that things are simpler. I know the group of transformations under which P0 as well as P1 would remain invariant. And that group of transformation is nothing but the additive group of transformation. So P0 and P1 are invariant under which is nothing but GC, C belonging to R, where GC of x1, x2, xn is nothing but x1 plus c, xn plus c. What is the induced group of transformations? With what should be G bar? G bar, you know that when it is in P0 or it is when it is in Pi, x1 plus c would have y1 minus theta minus c. So theta gets transformed to theta plus c. So G bar fi theta, that is what is happening, because your functionals are f1 theta, f0 theta, and theta is varying. So G bar of fi theta is nothing but Fi of theta plus c. I is equal to 0, 1. So I know, so I first try to look at what is my invariant statistic. What is the functional form of an invariant statistic? So Tx is invariant under G if and only if T of x1 plus c, xn minus 1 plus c, xn plus c is same as T of x1, x2, xn for every x belonging to Rn and c belongs to R, which is equivalent to saying that I have 1 degree of freedom, which is in terms of manipulating with c. So I can take c to be minus xn. So this implies that T of x1, x2, xn is same as T of x1 minus xn, xn minus 1 minus xn, and 0 for every x. So what does that mean? T is invariant. That implies that T is some function of x1 minus xn, x2 minus xn, and xn minus 1 minus xn. So which is equivalent to saying that T of x1, x2, xn is same as V of d1, d2, dn minus 1. Where what is di? xi minus xn. Right? That you have gotten from here. Converse is also true, because if any statistic which is function of d1, d2, dn minus 1, if I apply x1 plus c, xn plus c, in di it will become xi plus c and xn plus c, cc would get cancelled, so di remains as it is. So T of x1 plus c, xn plus c would be same as V of d1, d2, dn minus 1, which is same as T of x1, x2, x. So this suggests that a statistic is invariant if and only if it is a function of d1, d2, dn minus 1. So what does that mean? That means the maximal invariant statistic has to be a function of d1, d2, dn minus 1. This implies that d, which is d1, d2, dn minus 1, is maximal invariant. Where di is nothing but xi minus xn. Now, what would be the maximal invariant statistic? Sorry, maximal invariant functional? Would satisfy that g bar of theta of g bar of fi theta of fi theta. I should have used some other theta. So it would be same as theta of g bar of fi theta. So it is g bar c. I should put here g bar c, right? Because which is same as how much? Fi of theta plus c for every c. What does that mean? That means c I can take as minus theta. So this implies that theta of fi theta is same as fi 0. So that means just theta vanishes. Just theta vanishes. So that means the distribution of this will only depend on this function, theta of fi 0, which is f1 0 or F0, 0 or F1, 0. So theta is not going to play a role, which makes sense because under H0, you know that distribution is this, and I can take theta to be 0 because of x1 minus xn and xn minus 1 minus xn. So that corresponds to testing whether my data is coming from F0 or not, because theta becomes 0. So only F0. So you can look at under HI, the joint PDF of D, which is D1, D2, Dn minus 1. It was Fi theta, but I can take theta to be 0. So HID is how much? Minus infinity to infinity. It does not depend on theta. If you want to keep it theta, you can write down theta, but it doesn't matter. D1 plus T minus theta, Dn minus 1 plus T minus theta, T minus theta dt. Right. What you do is you make the transformation that D1 as x1 minus xn, D2 as x2 minus xn, Dn minus 1 as xn minus 1 minus xn, and last one as it is. That means x1 becomes d1 plus last one minus theta, x2 is xn minus 1 is dn minus 1 plus last one minus theta, last is remains as it is. And then I integrate out the unwanted variable, which was the xn, which was the last variable t. So this is the joint PDF of d1, d2, dn minus 1. Now I can put t minus theta as something. It becomes fi of d1 plus t, dn minus 1 plus t, t dt. So note that your phi belongs to di alpha if and only if distribution of phi depends on HID. Distribution of phi, which is invariant, depends on HI, which is under F0 or F1. And under H0, so what you have is H0 that your H is same as H0, and H1 is that H is same as H1. So what you know is F0 corresponds to H0 and F1 corresponds to H1, because I corresponds to I over here. So that means F0 would correspond to H0, F1 would correspond to H1. Now since F0 and F1 just go in the background, everything depends on only now on H0 and H1. And F1 and F0 play the role through H1. So my null hypothesis has been transformed to that H is same as H0, H1 is same as H is same as H1, because my invariant test has to be a function of d1, d2, dn minus 1. Distribution of d1, d2, dn minus 1 depends on Fi only through HIDs. So my H0 star gets converted to this. But what is this hypothesis? This is a simple hypothesis because there is no theta. It says HID is completely known. There is no unknown parameter. So what it amounts to? It amounts to testing simple versus simple. That, see what has happened. With invariance, you have reduced the data from x1, x2, xn to d1, d2, dn minus 1. Null hypothesis has transformed to that d1, d2, dn minus 1 has a distribution h0. Alternative hypothesis has transformed to that distribution of d1, d2, dn minus 1 is h1. But h0 and h1 are completely known. So it is simple versus simple. So one can talk about uniformly most powerful alpha test. So what is the uniformly most powerful alpha test? UMPI alpha test. So UMPI alpha test using Neyman-Pearson lemma, because Neyman-Pearson lemma gives you the most powerful test for testing H0 against H1. When H0 is simple and H1 is simple, as phi star x, which is 1, if H0 upon H1 is greater than, H1 upon H0 is greater than C. H1 upon H0 means minus infinity to infinity, F1 d1 plus t, dn minus 1 plus t, t dt upon H0, which is same as minus infinity to infinity F0 d1 plus t, dn minus 1 plus t, t dt is greater than C. You can put it here gamma u, if this is equal to this. In absolutely continuous case, this gamma u has to be normally 0, not always, and this is 0 if this quantity is less than C. And where gamma of u is chosen, so that actually this would be gamma of d, so that E f naught phi of x. F naught means basically under H naught, right? Because your distribution, the distribution will depend on F naught only through H naught. This is same as alpha. So you could see that this invariance principle turns out to be very useful in reducing the data. As a consequence, in finding the best test among tests having a nice structure which is invariant. We applied to the location family where we are interested in testing whether your data is coming from a one location family against that it is coming from some other location family, like normal versus Cauchy. In such a situation, I was able to find UMPI alpha test. Note that finding uniformly most powerful tests may not be that easy. I can repeat the same thing for the scale family. I can repeat the same thing for affine families or location scale families. Only difference is group of transformations would change as we did in the estimation case. So what I'll do is in the next module, I'll repeat it for scale family and then affine families. So that's all for today. Thanks for your patience.